The name Beckart is a tough one for us Brits because of the strange spelling, the A followed by the E. It's not meant to confuse anybody. It is the name of the founder of the company. So Leo Leander Beckart started the company in 1880 just as a one-man band. And the product that he produced was barbed wire for the agricultural industry in the Flanders region of Belgium. Now there may be a tiny delay while I load up a video.
Steel wire. We transform it, apply cutting-edge coating technologies, and specialize in continuously improving any property of steel wire products. Explore the world of Beckart. From wire rod, we draw steel wires even as thin as 1 micron. We bundle them into cords or strands or ropes and can process them into an end product. We design and coat them to meet your specific requirements. So whatever your sector and your needs, Beckart can develop the perfect wire. From specialty steel wires and cords for automotive component and tire makers, over solutions for agriculture or the construction industry, to leading technologies for the energy and extraction sectors, the numerous applications of Beckart products are as unlimited as your imagination. We co-create with you. It's the core of our corporate philosophy, better together. Whatever your need, wherever you are, Beckart is present all over the globe. We're committed to assist you with our local support and services whenever you need them. We aim to be your preferred supplier by delivering superior value in everything we do. Before any Beckart product reaches you, its quality is assured thanks to extensive testing. And that's how we've created a legacy that stretches over 130 years. Every day, we continue to build on this experience and increase our expertise in our world of wire.
Okay, so hopefully everybody's got the sound now. I've noticed a few people saying they've struggled. Alacio, who is one of the people who's joined, has pointed out, watch this via Chrome. That's the way to get it to get the best audio and visuals. Okay, so the next slide. An overview of the company Beckart. Since 140 years now, I think it is. We now gone from 1 employee to 30,000 around the world. Largely those people are in production. We're in over 120 countries and our turnover is just shy of 5 billion euros. Like I say, it's not just building products that we make. If you can see these slides, champagne cork wire, for example, is a niche market of 5,000 tons per year. That's a lot of fizzy wine. Our largest industry is automotive, and the biggest product that we make there is reinforcing cord for rubber tires. We actually have a 25 to 30% market share of that worldwide. So we like to say that we've reinforced a tire on average on every single car in the world. Then there's Dramix steel fibers, but also other things like solar panels and even simple wires for book binding, that sort of thing. You can see here automotive accounts for around 43% of our sales, but the second largest sector is construction, and that's what we're here to talk to you about today. These are our building products. So on the left-hand side, you can see Dramix steel fibers. That's what today's talk is about. The other products that we have, other than reinforcing concrete, can reinforce asphalt roads, masonry, and plastering. If anybody is interested in seeing a webinar about those products, please let us know separately and we'll arrange that accordingly. Some of the applications that we have for reinforcing concrete are as follows. Industrial floors is our day-to-day product. Tunnels and mining are usually our largest projects that we have. These are our production facilities. So most of the fibers that we use in the UK and Ireland are actually manufactured at our plant in the Czech Republic, which is the largest steel fiber plant in the world. But also we produce in North America, South America, Asia. You'll see here some examples of Dramix steel fibres that we produce. Now, 3 of those photos look very similar. Well, one of them you can see on the bottom right-hand corner of those 4 shows you the basic shape and size of Dramix steel fibres. What you'll see there is these are loose fibres. Now, the steel fibres can be loose or they could be collated in bundles, as you see on the other photos. There is a reason for that to aid the mixing process. The whole principle of steel fibre concrete is completely different to traditional. Steel fibres are added to concrete to provide a ready reinforced concrete material. And the idea is that it is 3-dimensional. So there is no concrete cover. The fibres are mixed throughout the whole concrete mix, providing a matrix of steel wire, giving 3-dimensional reinforcement. The idea of having 3-dimensional reinforcement is that when concrete exhibits an initial yield, there will be fibres inside that concrete mix. And the idea is that they will bridge a crack and transfer stresses from one side to the other. Now you can imagine these steel fibres, depending on the fibre type or the dosage, they usually count for around 100,000 fibres per cubic metre, and sometimes more. The idea being that there will be such a network of reinforcement in there that when there is this initial yield, there will be reinforcement in the locality to do so. Lots of different things are affected in concrete by the addition of steel fibres. The most important one really is increased toughness. This can also be called ductility or post-crack strength. And we'll be covering that in depth today. But also things like shear resistance, impact and fatigue resistance, these are all increased as well. There are a number of different factors that affect how high or low performing a steel fibre is, and these are going to be covered in the next few slides. The first one is the tensile wire, the strength of the wire, okay? Most of our steel fibres use a tensile grade of wire of anything from 1100 to 2300 newtons per square millimetre, so at least twice that of traditional mesh. If these steel fibres with this shape were made from 500 Newton grade wire, just like mesh or rebar, then they would fail in the concrete. The second important factor is the anchorage mechanism. So this is effectively the shape of the fibre. If you could see these three fibres on the screen, Dramix 3D, 4D and 5D, they all have different shapes. The idea is that these shapes are called anchors and they lock into the concrete to provide concrete ductility. This slide shows the 3 different fibre families that we have, Dramix 3D, 4D and 5D. Now, a little bit of history. Dramix 3D is the original Dramix. So we've been making that in Belgium and overseas since 1975. And in 2012, Dramix 3D was called simply Dramix because there was no other type. It is a straight wire fibre with hooked ends on the end, a simple hook end. What we can see here is the effect of having a single fibre embedded in concrete, 50%, and then pulled out of the concrete. What you could see with an individual 3D fibre is that it would take a force of around 300 newtons for that fibre to yield. And the failure mode of that shaped fibre is that the fibre, if you apply enough force, will pop out of the concrete. Okay, so the anchor would deform, the fibre would become completely straight, the fibre would then pop out of the concrete and stop providing ductility to your concrete. Dramix 4D was developed after a 3-year research and development program between 2009 and 2012. And you can see the failure mode is actually very similar to that of the 3D fibre, but you actually need a much higher force to start that elongation of the anchor. So 500 newtons to see the fibre start to pull out of the concrete. So the 4D fibre has the same failure mechanism, but it takes a greater force for it to actually happen. Dramix 5D, which has an extra wave on the end, actually works in a completely different way. It is a bit of a one-off in the market. You don't actually see that fibre start to yield in any way until you've applied a force of around 1200 newtons, which is obviously around 4 times that of the Dramix 3D. But the failure mode is different. The anchor is actually 100% efficient, so the anchor will not move. It will remain embedded in the concrete. What happens to the straight part of the wire is the yield will occur there, but in order to stop that fibre from snapping, we use an ultra high tensile grade of wire of 2,300 newtons. What that wire does is it has an elongation capacity, so it has a certain percentage allowance to actually allow that fibre to stretch without breaking. So the failure mode of Dramix 5D is completely different, and that gives us different ductility values because of that. Here we can see the effect of the pull-out test, the sort of wire that we make these fibres from, okay? The third thing is the aspect ratio. Now, this is the length divided by the diameter of the fibre. That gives you a number. The higher that number, the more fibres you have in your concrete mix, so the more dense of a wire matrix inside your concrete. For example, you can see on the right-hand side, we have 3 different Dramix fibres there. They're all from the 3D family, so they all have a single hook on the end, but they all have different aspect ratios. So they're different lengths. One of them's 50, the other 2 are 60 millimeters, but they're drawn to different diameters. So if we look at the 3D 4550 BL, that is a 50 millimeter long steel fibre with a diameter of 1.05, giving it an aspect ratio, rounded down, of 45. If we have a 60 mil long fibre, draw it down to 0.75 mil diameter, what you actually get is you get a lot more fibres per kilo, which means you have a much denser network of steel inside your concrete. And you can see the actual network of wire you have in a cubic meter of concrete, if you look at the last row on that table, is twice that of the 4550. The fourth thing, homogeneous fibre distribution. Now you can see on the photo in the center there, we have 2 examples of fibre addition. On the right hand side, what you see there is a high aspect ratio fibre that's been added to the concrete in loose format. And what you see on the left-hand side is the same fibre that's glued together in bundles. Now, one aspect of high aspect ratio fibres is that you get higher performance. The downside is that workability is decreased and it becomes more difficult to work with that fibre. If you have that fibre in a loose format, you have a tendency for the fibres to conglomerate and you get what you could call a steel hedgehog being added to the concrete, which is very, very difficult to then mix in the concrete and impossible to pump. The way that we make the addition of these easier is to collate them into clips using a water-soluble glue. The principle being that the fibres are added up on a simple conveyor into the concrete. As soon as the fibres hit the mix, the water in that mix breaks down the water-soluble glue, and then the fibres disperse in the concrete. So it's important to know if you use a high-performing fibre, if they are glued, they will mix a heck of a lot better. The fifth thing is third-party conformity. Now, every single pallet of fibres used in concrete in Europe, including the UK and Ireland, has to be accompanied with a CE label. This label will give some basic physical properties of the fibre and also some basic test data. Now, you can see in the center of the screen there, you can see the EN beam test. This is used to work out the ductility of fibre concrete. Okay, there will be some basic details of this test on the CE label. We'll go into this test in more detail later on. Now, here's some basic principles of concrete behaviour when you have fibres added to it. Now, if we start on the left-hand side, plain concrete. If you have a sample that's loaded centrally, simply supported, at some point that concrete will crack because it has no ductility, then you'll get instant brittle failure of the sample. If you add fibres to this concrete, SFRC is steel fibre reinforced concrete, what will happen is you will not increase the first crack strength of that sample, but you will give it post-crack toughness. So what happens is the fibres will not increase the strength of the concrete until there is a yield, but then it will stop that sample from failing. If you have fibre concrete and some traditional bar in there as well, what you will get is effectively a bending hardening situation, which is something important to remember in a few slides' time. Basic design principles. Well, certainly when designing an industrial floor, for example, to the ultimate limit state, this means you're applying various factors to the materials and to the loads. And what you will get there is you will get a capacity of your actual as-built concrete is far greater than the theoretical capacity. So it's important to know there is a lot of safety built into these designs. We also run serviceability limit state checks, which don't take into account any of the loadings or anything. They're more to do with the deflection, shrinkage, and crack openings of the concrete. This is the setup of the EN test. In the past, steel fibre ductility was measured using a Japanese or American test, but this has been largely superseded in Europe by the European standard, EN 14651. That sample of concrete is 550 millimeters long, with the simple supports spaced at 500 millimeters and a single point load applied to the top. What you will see from the graph is that we measure 4 different increments after the cracking. You might be able to make out the lettering along the x-axis of the graph, CMOD. This stands for the crack mouth opening displacement. And what we do is we plot 4 different locations on the x-axis to get FR1, FR2, FR3, and FR4. So these are levels of ductility that are achieved by this sample, reinforced with steel fibres at different increments, different openings of the crack. You can see the basic principles of the 3 different fibre families. So Dramix 3D has been around for a long time, and you can see that depending on the dosage that's used, a ductility level of between 60 and 70% is quite achievable. Dramix 4D is very similar in performance, but it gives a higher level of performance. So as we explained with the pull-out test, the failure mode is the same, but the levels of ductility that we add to the sample is increased. Dramix 5D, on the other hand, works differently. Again, the same principle remains. The first crack strength is not increased, but what you will get after that first crack is an increase in the capacity of the concrete. So what we're getting is bending hardening. This is the ability of the concrete to be stronger after it's cracked. And you can see there's some real life examples of the 3 different fibres that are tested to the EN beam test. If you have any more questions about these, please ask at the end in the comments section and we'll try and answer them. Now I'll be loading up a quick video. There'll be a slight delay. Please bear with me. A longer delay than I anticipated, admittedly.
Concrete is naturally brittle. Typical stresses like impact, fatigue, and loading lead to cracking and eventual failure. Adding reinforcement to the concrete helps to absorb these stresses and to limit the formation of cracks, increasing the load-bearing capacity and ductility of the concrete structure. There are several ways of reinforcing concrete. We've all heard about rebar and steel mesh, but did you know steel fiber is just as strong and reliable? Since its introduction over 40 years ago, steel fiber reinforcement has proven its merits in the most demanding structures and applications. The core difference between steel fiber and other reinforcement solutions is that fibers are part of the concrete matrix, turning it into a composite material. Instead of providing strength in distinct locations, steel fibers form a reinforcing network throughout the entire concrete structure, increasing its overall ductility. So how does this translate into concrete behavior? Take a random concrete structure. When subjected to loading, compressive and tension stresses start to build. Over time, small cracks will appear in places where the stress reaches a critical point. Steel fiber interacts within the concrete matrix, absorbing tensile stresses at any point and in any direction. As a result, steel fiber picks up small cracks much faster than traditional reinforcement. When a crack occurs, the hooked ends of the fibers remain solidly anchored on each side of the crack, acting as a stress transfer media. Once the maximum bond strength with the concrete is reached, the pull-out takes full effect. This enables the next fiber to take over, delaying cracks from growing. Different loads require different steel fibers. To meet any design requirement, Beckart offers 3 steel fiber types: Dramix 3D, 4D, and 5D. Each fiber has a different hook, strength, and ductility. Consequently, they also behave slightly differently when dealing with stresses. Let's take a closer look. First up is Dramix 3D. When a small crack occurs, the 3D hooks firmly anchor inside the concrete matrix. As the stress increases, the hook slowly deforms. As soon as the fiber loses its bond with the concrete, the pull-out takes full effect. Dramix 4D provides the same process, but with even better anchorage and a significantly higher tensile strength of 1,650 Newton square millimeters or more. Dramix 5D behaves differently altogether. Here, the hooks never pull out from the concrete. As the stress increases, the wire slowly elongates until it reaches its maximum strength. With a tensile strength of 2,300 Newton square millimeters and elongation of 6%, concrete structures reinforced with 5D can take high flexural stresses over a long period. Based on these behaviors, we can conclude that Dramix steel fibers effectively increase the load-bearing capacity of concrete. It can be used in almost any concrete structure with or without additional reinforcement, where the ductility of your concrete structure depends on the length-diameter ratio of the fibers and the number of fibers used per cubic meter. It is essential that enough fibers overlap to create a continuous network in the concrete mix. Do you need help finding the right fiber and determining the right dosage? Beckart gladly provides expert guidance through each step of your project from design to execution. Visit www.beckart.com/Dramix to get in touch.
David, are you still mute, David? Because we can't hear you.
I can see I've just made an error. My speaker is now on. I'll start the
Yes,
slide
I
again.
can hear you again.
Okay. The applications that we have in the UK and around Europe are as follows. Slabs on grade and floors on piles. These will be covered in quite a lot of detail by both myself and Ben. But other applications, precast tunnel linings is a very large application for us around the world, particularly in the UK. Precast structures, other ones such as pipes, that's a big one. And a UK-centric application that we've had for nearly 20 years now is the use of Dramix on Kingspan multi-deck. Okay, so we can actually replace the steel reinforcement in concrete on metal decking by using Dramix steel fibers. If you have any specific questions about these applications, please ask them at the end of the presentation and we'll try our best to answer them. It's important to note that steel fiber concrete is suitable for some applications and others not. It's not suitable for statically determinate systems. For example, you can see that balcony on the left-hand side. You've got to remember the principle of the first crack is always the last crack in a statically determinate system. So you would need to use a combination of steel fibers and traditional reinforcement to reinforce any of these types of structures. So the applications that we have, this presentation will largely be tailored to suit industrial floors, but the principles remain the same for any application. It's important to know that. Here's a few examples of those applications. You can see industrial floors are quite prevalent on a few of these. On the top in the center, you can see something called a clad rack structure, which will get mentioned a little bit in this presentation. A clad rack A lot of you might not have heard of these, but they're quite new and quite in vogue with a lot of blue chip clients around the world now. It's the way of having an extremely dense network of pallets inside a building. If you can imagine a standard portal frame warehouse, the way that that is constructed is that the floor would go in last after you've got the steel structure up and the cladding on and the building weather tight. A clad rack structure is the other way around, in that the floor is also the foundation for the entire structure. And actually the structure is the racking system with some cladding and roofing stuck to the top and the sides. So it's done in a completely different way. Clad rack structures usually need a steel fibre reinforced floor of at least 400 millimeters deep to take the huge loads. But as well as the downward forces from the very heavy racking systems, you also have uplift in certain places from the wind hitting the side of the building. So this is a very good application for steel fibre concrete. What you can see on the bottom right-hand side there is a strange shaped building. I believe this is called the CCTV Tower, and it was built prior to the Beijing Olympics. Any concrete elements in that building are traditionally reinforced, but also they use additional steel fibre concrete, Dramix, to aid against seismic effects. So steel fibres have a lot of different applications of performance related issues. So what we're going to do now is talk about different industrial floors. We'll start off with the most common ones and the oldest type of ones, which is a saw cut floor. A saw cut is effectively a planned crack in your concrete. Concrete floors have a tendency to crack if you don't have joints at regular centers. So the way to stop uncontrolled cracks is to put a planned crack in its place. So if you see a warehouse or a factory with joints at 5 or 6 meter centers, this is probably going to be a saw cut joint. Okay, what this does is it helps the concrete when you get concrete shrinkage, and you need to relieve that shrinkage to avoid cracking. Here's a little example here. If you look at on the left hand side, you'll have a grid of saw cut joints, say on 5 or 6 meters. It's a small sample that you can see on the screen there, but if, for example, they were at 6 meter centers, you would have a panel there on the left of around 600 square meters. But you can see you would have a network of over 140 linear meters saw joints. Okay, that's important to know in a few slides' time. So a saw cut is the use of a saw that's drawn through the concrete to a third of the slab depth. The idea is that what it will do is it will induce a crack beneath it and allow the concrete to move. Now, why would you use a saw cut floor? Well, in some applications, they can be the cheapest way to reinforce a floor, usually quite a modest amount of reinforcement. And the idea is, as I've said, concrete will shrink. You need to relieve those stresses due to the concrete stress by inducing joints in there. The advantages are that you can hopefully minimize the amount of unplanned cracks that clients don't like because of aesthetics. And usually, as I said, it's the cheapest solution, but not always. The next evolution of floors that was able, due to lots of research and development of steel fiber performance, is jointless floors. The name is a little bit strange in that it isn't necessarily a floor with no joints, but it is large daily panels of concrete that are cast without saw cuts. So effectively, a jointless floor is a saw cut free floor. The reason jointless floors are popular with certain clients are that effectively the more joints a client has, the more long-term maintenance issues that client is likely to have. Forklift trucks driving over saw cuts, what you can get is you can get a lot of damage over those that will need repairing at some point. Quite often with these logistics facilities, they're 24/7 hour operations. They never really close down, and actually getting a repair contractor in there can be very difficult because these clients need constant access to the whole building. Here's an example of some problems that you can get with either cracked floors or floors with saw cut joints. So you can see on the left hand side a crack. That's a picture of a crack that has actually been repaired. But what happens with concrete is it will largely keep shrinking over a period of weeks and months, maybe even up to 2 years. And whilst it's shrinking, you're getting more and more crack openings. So if you repair a crack early, but the concrete continues to shrink, there's a chance that that crack repair may also fail. So if you can minimize the amount of cracks that you have in your slab, again, it's another long-term maintenance issue that's reduced for the client. Curling, this can occur in any concrete because you have a wet material that then goes hard, but the water's still inside there, and the water has to evaporate out of the top surface of the concrete over a certain amount of time. This can create curling. Rocking slabs is a phenomenon of where you have a joint that opens up too wide, and then you actually lose aggregate interlock from one side of the joint to the other. So rocking slabs mean that when you have MHE driving over that joint, you will actually get physical changes in the vertical movement of that joint. That definitely needs a repair. We've also got spalling joints and poor load transfer, which is similar to rocking slabs. These are all big problems for owners of buildings with concrete floor slabs. So a way around this would be to reduce or completely eliminate saw-cut joints in floors. This is what jointless floors do. Now, jointless floor, in theory, can be up to 50 meters by 50 meters in a single day with no intermediate stress relieving joints. Okay, 50 by 50 is 2,500 square meters. So often one thing that will dictate how large a jointless panel can be is down to the daily concrete supply that the contractor can actually get. Okay, but that is theoretically the maximum that we could do with no saw-cut joints. Here's an example. You can see on the left-hand side a saw-cut floor we've already described. A jointless floor wouldn't have any of those induced joints, but it would have joints separating separate daily jointless pours. Okay, and the way you do this is by having a dowel joint profile, such as alpha joint made by Permaban. So what this is a leaving place permanent metal formwork joint. So this isn't like a timber shutter that you have to strike and remove the following day. This stays in place for the life of the floor. You can see that it doesn't have traditional dowels. It has a trapezoidal plate dowel that gives load transfer from one side to the other. And also it has two steel plates at the very surface of the floor that reinforces what would ordinarily be a bare joint concrete arris on the surface. Okay, so it gives protection for when mechanical handling equipment drives over it. The next evolution above jointless floors is a seamless floor. Okay, so a jointless floor really is a floor that has no saw-cut joints, but a seamless floor is a true floor without any joints. Now, when I say any joints, obviously some buildings are way too big to actually cast in a single day. But what it does mean that joints between daily panels can actually be tied traditionally, so that there'll be no joint openings in the building whatsoever. So I've already explained to reduce the amount or eliminate the amount of saw-cuts you have on the floor is a big long-term maintenance positive for a client. But actually to have a floor with no joints whatsoever, no joint openings, gives the client a lot of future flexibility. It means that they can put their racking systems, their shelving units, or their mezzanine floors pretty much anywhere. Whereas if you have lots of joints, the actual positioning of these pieces of equipment can often be compromised. Now, it's important to know a seamless floor cannot currently be done with steel fibres alone. You need a combined solution, so what we would call a combi slab of traditional mesh and steel fibres, either a single or a double layer of mesh. Now, the basic principle of adding fibres to traditional reinforcement is as follows. So this is a diagram showing a restrained piece of concrete. What will happen is, with traditional reinforcement, you will get cracks. With a combination of reinforcement, you will still get cracks. In fact, you'll get more cracks, but the crack openings will be narrower. Okay, so there will be thinner cracks. That's the basic principle of adding the two types of reinforcement. At some point, the concrete will crack. Okay, and in order to get a calculated crack width in your concrete, it's dependent on the stresses being in the steel. Okay, so the addition of fibers to that concrete mix decreases the stresses in the rebar, allowing a reduction of the rebar that you need in order to get a defined crack width calculation. Important thing to note is that if you're going to design an industrial floor to a crack width, is that the higher the effective height of the concrete, so the thicker the slab is due to loads designed in the ultimate limit state, the more difficult it is to get that defined crack width calculation. Okay, so thinner slabs in general need less reinforcement, be it steel and rebar, than you would need in a thicker section in order to achieve the required crack width that a client needs. Very important to know. Here's an example of a job in Holland. Okay, and what we had here was the basements of this multi-story building. These basements needed to be designed for uplift due to water pressure from beneath. Okay, traditionally this slab needed to be 400 mil deep. These are European meshes with bars at 100 mil centers, top and bottom. Okay, no fibers at all. Now our alternative solution was a combi slab, so it still had traditional reinforcement in there, but it was the same slab depth, same concrete grade, lighter meshes, and 25 kilos per cubic meter of Dramix 4D. What you got from this was still the required 0.5 mil nominal crack width that the solution needed. Okay, but you can see the cost differential was 15 to 16 euros per square meter cheaper by reducing the amount of rebar and adding steel fibers. So why would you have a seamless floor? You have a lot of high-speed lift trucks in a building like this. So the less joints that they drive over, the less long-term maintenance that you will get. Lots of durability. You have the strength of both types of reinforcement in there. You have quality, no doubt about it. Cracks may occur, but they will be designed accordingly. And as I mentioned earlier, you get full flexibility for the client. If you have less joints or no joints, machinery and everything, that can go pretty much anywhere in the building. Typical applications for a seamless floor: distribution centers, clad rack warehouses, as I've already explained. The biggest one that we have in the UK, the biggest application for this, is for scrapyards and waste transfer systems. Clients like this system because it makes sure that they don't have these joints. When you have a scrapyard and you have a loading shovel, the abrasion resistance needed on the concrete is very high, and the joint damage that you'll get is also very, very high. Now, what we can do with a defined crack width is that we can actually design concrete elements to retain liquid, okay? Liquid type floors. Different applications that we have: the food industry, chemical industry, petrochemical. If you can imagine having a bund, for example, at an airport, the last thing the client wants, if they get an oil spillage, is for that oil to penetrate into the ground beneath. An application like that would need to be designed to a defined crack width. Also, floors with coatings. What's important to note here is if you were to put something like a polyurethane screed or a thin resin on top of the concrete, quite often these materials cost more than the actual concrete beneath. But if your concrete slab cracks, then that resin will also crack. It's called reflective cracking. So quite often with these applications, the concrete slab beneath needs to be designed to a defined crack width. Now I'm just going to take a quick 30-second break to find some power to plug in my laptop because it's bleeping at me. So just give me a second. Apologies for this. And there we go. Floors suspended on piles. This is a huge application in the UK, largely because we have a lot of coastline and therefore a lot of poor ground. Now, what do we mean by a floor suspended on piles? Well, we see this as a true structure. Admittedly, it's a ground floor structure, but still we can't take any enhancement from the ground beneath. So it's a floor that is suspended from pile to pile that quite often has to take quite heavy loads. And you can see there. Now, why would you have a floor on piles reinforced with steel fibres? Well, usually the alternative would be to have a heavy congestion of traditional steel. You can see with the top photo, what you get there is usually days and maybe even weeks of steel fixing that's required before you get any concrete down. And because of the congestion of steel, particularly with the steel being in the top as well as the bottom, you can't direct discharge concrete from trucks. You would need to pump, which is not a problem, but again, it adds to the financial elements and also it slows down the process. By using steel fibre concrete, it's possible to eliminate a pump in some cases, in most cases, and usually it can be done cheaper and quicker, but with the same performance. There's three different solutions that we have for floors on piles. If we actually start on the right-hand side, the solution that we've had for a long time is to use Dramix steel fibre reinforced concrete in combination with a continuous layer of traditional steel. And this still exists now. We still do floors like this. But this evolved thanks to our friends in Holland who developed a structural code specifically for floors suspended on piles and reinforced with steel fibres. And what they decided was that traditional steel was placed where it was actually most needed. They analysed that sagging moments between piles were very rarely the failure mode, and actually hogging moments over the piles or punching shear was the theoretical failure mode of these floors. So you can see fibre reinforced concrete, but with a lot less mesh. The next evolution of solutions is to get rid of all the traditional steel completely and just have a purely fibre only solution. So there's the Dutch system with localized mesh over the piles. You can see much less congestion of steel makes the system much quicker. This is the system that we've had for a couple of decades. Traditional mesh throughout, however, reduced by anything from 40 to 60% over what it would need to be if it was fully traditionally reinforced. So you can see that's fibre reinforced concrete being pumped to the workface over the mesh. So, as I've already mentioned, steel fibres can be used in floors on piles, and it is a prevalent application in the UK where a lot of the subcontractors much prefer to use steel fibre concrete nowadays because of the savings in time and money. This is a worked example, but a real example. So this floor on the left-hand side, you can see it needed to be 300 millimeters thick, designed for a UDL of 40 kilonewtons a square meter with top and bottom reinforcement, okay? If you have that sort of a solution, you need to fix the steel before you can do anything, which usually takes a few days, as I've said, and then the amount you can actually pour, or I should say pump per day, is quite modest. The three solutions that we have, as I've already discussed, are as follows. We'll start on the right-hand side again. Combined reinforcement, so Dramix 4D and a continuous top layer, so not two layers, just in the top. That would need to be 240 millimeters thick, and we're looking at a pour area of substantially larger than the traditional scheme. The next one would be the Dutch style system with Dramix 5D and localized mesh. That again could be thinner than the traditional scheme, designed to the same code and standard, but with substantially less traditional reinforcement. Therefore, the daily panel size could be larger. Bigger panels means less days on site. And then due to the power of Dramix 5D and its bending hardening capabilities, the third solution on the left-hand side would be fibre only, same thickness as traditional, but with vastly greater daily panel sizes. That says over 1,600 square meters. Again, you might be limited by the amount of concrete you can get from the local batching plant, but the principle remains. 1,600 to 2,500 square meters per day, certainly possible with fibre-only solutions. Here's a cost and time analysis of those three solutions. Now, we're not here to tell you that getting rid of traditional reinforcement completely is always the answer. And actually, you can see on this work solution, the cheapest solution wasn't necessarily the quickest. It was actually the Dutch style system with the minimized local reinforcement. That worked out at an overall cost saving due to saving in materials and also time on site of 28%. Now, here's another project that we can look at. The less days on site, the less joints, the less panels, more savings. So we have an example here, a 120 by 120 meter floor That's about 14,000 square meters. If it's traditional, what you would need is joint centers of, it says 30 meters maximum, and that really would be the maximum. Quite often it's much less than that. So that would require 16 days on site just to pour. That's not forgetting all of the steel fixing that needs to be done beforehand. And that 14,000 square meter floor would need around 720 linear meters of joints. To use a steel fiber solution, you'd have less days on site, larger panels, less joints, less long-term maintenance issues, and an overall cost saving for the project. The conclusion is that we can design any pile floor depending on the parameters with any of those three solutions. So the main reasons for choosing these solutions over each other would be if you went for the combined solution of Dramix 4D and a full layer of mesh, the main reason you would do that would be that you could design that to a defined crack width, which is an advantage of using the combined solution. If you were to use Dramix 5D and the top mesh squares developed in Holland, this can be the most cost efficient, particularly if you use small precast piles or if the pile spans are large. Important to know that. But if the pile spans are fairly moderate, say under 4 meter centers, and particularly if you have piles with pile caps or enlarged flared heads on the piles, a fiber only solution, because it's the fastest, can often be the cheapest as well. So it's important to look at every single project on its own merits. Those solutions can give different advantages, both in performance and cost saving over each other, depending on loadings, pile type used, pile span, and client requirements on crack width. There are some limitations on these fiber floors suspended on piles. You're looking at a maximum grid size of 6 meters. Most economical will be between 3 and 4 meters. Okay. The joint distance, you're limited to 50 meters, but you think about it, if you had a 2,500 square meter panel and it was 300 deep, you would need 750 cubic meters of concrete, which is a tough ask from many ready-mix suppliers in the country. So quite often we are dictated by the actual local supply. Here we see a diagram of a floor of around 11,000 square meters, so 120 by 95. And you can see that the daily panels are split up by the use of a leave-in-place joint. That one that you see there is called signature, which is similar to the alpha joint that I explained earlier. Okay, and we have panel sizes there of around 40 by 40. Okay, so call it 1,600 square meters per day. So that 11,000 square meter floor will be poured in 6 days. Extremely economical. Don't forget, no steel setup beforehand if it's 5D only. It means that the amount of preparation before you actually pour is minimal. The next solution that we have on top of that would be to use Dramix 4D and traditional reinforcement. This is something important to note, that you're not limited to 50 meter long panels, and you're not limited by aspect ratios of your panels. They don't need to be square. They can be long, thin, and in theory, you could even go up to that full 120 meter length in a single day if you could get enough concrete. Applications for floors on piles, just the same as ground bearing ones really. Distribution centers, factories, cold stores, warehouses. Important that we look at different types of fibers on the market. So I've talked to you about steel fibers today. Fibers that have been around for a couple of decades as well. On the right hand side, you can see microsynthetic fibers, and these are extremely small, tiny diameter, millions of them per kilo, therefore tens of millions of them per cubic meter. Okay, they can be added to concrete and aid against early edge plastic shrinkage cracking, and sometimes they can replace air entrainment agents. So they have a couple of advantages that you cannot get with traditional steel or steel fibers. But after the first 24 hours after concrete has been cast, those fibers stop doing their work. They don't add long-term ductility to the concrete. They don't replace steel. It's important to note. What's also important to note is, though, that they can be used in combination with steel mesh or steel fibers because they do a different job. The other type of plastic fiber on the market are macrosynthetic fibers, which are effectively plastic fibers that try to copy the shape and size of steel fibers. So have a look at a bit of the analysis of the different materials that these are made from. It's important to note the Young's modulus of steel in comparison to that of plastic. The Young's modulus of synthetic fibres is actually less than that of the concrete they're trying to reinforce. And the melting point of the plastic fibres is very, very low. So as a summary, we can see what different fibres can actually do inside concrete. So microsynthetic fibres can do something that steel cannot: aid against early age plastic shrinkage cracking. Very important on external concrete. If you're laying external concrete that doesn't have polypropylene fibres in there, you may get unwanted early age plastic shrinkage cracking. Okay, but after that, they don't add any strength to the concrete. So you can use steel fibres to reinforce your concrete due to the loads, or because of your serviceability limit state design. But polypropylene fibres cannot do the same. Macrosynthetic fibres could be used in the ultimate limit state design, but they will add substantially less ductility than steel fibre reinforcement. Now, one thing that we get asked quite a lot is how do you ensure the homogeneity of steel fibre concrete, because we're adding the reinforcement to the concrete mix. And one thing, after a large investment and research and development scheme that we've created, is something called the ID solution. Okay, I'm going to share the final video of this presentation now, just to give you an idea of what it can do. Again, a slight delay, but it will work.
You don't take chances on the safety and integrity of your concrete structures. Checking the quality of your concrete reinforcement is therefore an important step in the building process. To perform a thorough and accurate total quality control and to exclude all human error, Beckert developed Dramix ID. Dramix ID is a measuring device that connects to the chute of concrete trucks. It analyzes the homogeneity and distribution of steel fiber reinforcement in concrete mixes. The data is measured at the chute and can be monitored in real time on your tablet or smartphone via Wi-Fi. Traditional quality control methods like washouts are known for being considerably labor-intensive and time-consuming. The automated system is simpler to use and provides a more accurate analysis of the distribution of steel fiber reinforcement in your concrete mix. The device continuously analyzes the concrete as it goes through the chute, allowing you to intervene immediately in case of inconsistency. You can instantly monitor the data generated by the Dramix ID on a mobile device via Wi-Fi. The data is also transmitted to a central server, where it is translated into clear, standardized graphs which are bundled into a report. You can consult this report from any internet-connected device and download the report from the central server as proof of the reinforcement's compliance with the norms. Dramix ID gives you peace of mind when it comes to the quality of your industrial concrete structures. Don't take any chances. Take control. Trust in Dramix ID. Visit our website at www.beckert.com/Dramix-ID.
I was a little bit keen there, I think. I cut off the tail end of that presentation. Okay, we're coming to the end now. One thing that I want to talk to you about is the benefit of working with ourselves, because we can actually give design guidance to you by using our software tools. Important to remember is that for every single country, there are different guidelines and codes that can be used. So our actual tools that we've developed encompass any of the local standards and codes. So for example, in the UK at the moment, Concrete Society Technical Report 34 seems to be the guideline that most people use, but overseas it wouldn't be. So we have options to design for all of these. Now, before we talk about our own in-house tools, it's also important to know what's actually out there for you as engineers that you can use to design elements with different types of reinforcement. You can see three different names there. Adapt is actually something for the North American market, but for Europe, a company called SEER have developed a finite element analysis package. And by using that, it actually uses a database that incorporates all Dramix performance related information in there. So you can design any concrete elements using traditional reinforcement, steel fibre reinforcement, or a combination of the two. And thousands of European engineers have this now, including in this country. The tools that we have that we've developed as Beckart are plentiful. You can see from there, we can design pretty much anything that involves concrete and fibres. The ones that I use personally are the slab on ground, slab suspended on piles, and also the bending moment capacity tool. You, as external engineers, now have access to these tools if you so wish, with the caveat that we come and we train you for a few hours just to show you what to do. They're all Excel based, all very simple to use. Anybody who's interested in getting access to these, by all means, get in touch with us separately. We can talk about that. Okay, that is the presentation. Session 1 now closed. And I think it's important that we field some questions now that have been posted in the chat. So over to Stephen.
Thanks a lot, David. Yes, there are already a couple of questions. Let's maybe start with the first one, and if anyone else has another question, please feel free to fill in the chat. The first question, David, is one about warranties. Do we offer warranties for our slabs on ground where we are involved in?
Yeah, this is a different one from country to country. We do have professional indemnity, so any guidance that we give or any designs that we give you are covered by our PI, which is important. But you find that in the UK, because most contracts are design and build, usually a contractor or subcontractor is responsible for everything. So what often happens is that they would have to provide a warranty. So their PI will go back to back with our own. That's how it works in the UK. So yes, we do have a warranty for our designs, but ultimately the all-encompassing warranty that's needed in the UK usually lands with the project engineer or the specialist subcontractor who's casting the solution. So there's an answer. Yes, we do, but it's not that simple in the UK. Surprise, surprise.
Thanks a lot. A second question is about the NHBC. If we have an accredited method to calculate the moment resistance with steel fibers, and as such use it in constructions that are under the umbrella of the NHBC.
Well, everything's acceptable to the NHBC if you do some dedicated testing with them or for them, which obviously comes at a cost. So for various NHBC applications, housing, beam and block floors, that sort of thing, I know for a fact that they would accept steel fibre reinforced concrete, but we would need to do a large scale testing regime with them in order to get their okay. So whilst they say they won't accept it, it's only because we haven't pursued it.
Thanks a lot. Then the next question about the sustainability of steel fibers when using them together or as a replacement of rebar. Are there advantages on, for example, the carbon oxide exhaustion or not?
Well, regarding design, obviously, if you can save concrete, that's the biggest emitter of CO2. So that's one way that we can do that. If you're talking about material against material, we do have information on the CO2, the embodied CO2 in the production of steel fibers. And also we can do a project by project analysis for you if you so wished, analyzing the CO2 of a traditional scheme versus a fiber scheme. So that is something that we can do. We have some off the shelf data for you if you so wish, although it's very basic. If you needed us to look into it further, we can do so.
Yeah, and I think a next question is maybe also answering a part of the previous one. How does the steel tonnage, so traditionally, compares with a design with Dramix fibers?
Yeah, most elements, particularly floors, compared to a traditional scheme, use a lot less weight of steel, a lot less. I was speaking to a client recently, and they had a job where per day they would have to tie and fix 44 tons of traditional mesh per panel. The Dramix solution was, I think, between 10 and 12 tons of actual fibres that was needed to achieve the same performance level. So I've never seen a job where there is more Dramix used than mesh. It's always a saving in that respect.
Okay, and then I think maybe one more. Huh? What are the advantages of fibers over rebar in composite floor slabs? Huh?
Yeah, the solution for Dramix used on Kingspan Multideck was developed by doing fire tests, and then the load span tables were developed with the Steel Construction Institute. So the main advantage of using steel fibers on a deck is due to health and safety. You have less craneage, less lifting, particularly in inner city projects where you have people below or busy roads. What you can actually do is add the reinforcement at the batching plant, deliver ready reinforced concrete to the site, and then pump it to the workplace. There isn't so much need for lifting large volumes of mesh to the workplace. So that's the main advantage. The design principles are quite different to a ground slab.
Mm-hmm. Thanks a lot. And maybe one last one to finalize this session. But if you have in the meantime more questions, we can treat them, of course, in the afternoon in the second session. The last one is about the ID system. If we offer it for free of charge, or if it would be needed to be purchased by the concrete supplier, for example.
It's not for sale, but it's available on license to independent test houses. So the idea of the ID system is that it generates results for the end user or the client. So it's not really for use by the specialist flooring contractor or the ready mix supplier. It's a check that the client can have directly for themselves. So we have approved users of the ID system. And that's how we've positioned it at the moment. So no, it isn't available to the market. It is, but it's available via approved users.
Okay, thanks a lot, David. Thanks a lot, everyone, for joining. So in the afternoon, the session will be mainly focusing on the technical behavior of steel fiber concrete and how you can design structures with it. And in the meantime, yeah, if you have questions, feel free to send them to us. We will try to answer everything, of course. And have a nice lunch and see you later.
Bye.
Bye-bye.
Bye, everybody.
Bye-bye.